everybody. Let's get started. Welcome all to this third YCI seminar on geoengineering this semester. We're very lucky to have Professor David Keith here today from Harvard University. The reason for this early and somewhat unusual time for a seminar is that he's given another seminar this afternoon, actually, on the ethics, I believe, and politics of geoengineering. And so I wanted to also advertise that talk for those of you who are interested in that. And so that is at the ISPS, which is on the corner of Trumbull and Prospect at 4:15. And if you want directions to get to that talk, you can also contact me. So let me briefly introduce David. David got his PhD from MIT in physics in 1991, and after that got one of these NOAA Global Change Fellowships, spent some time at Carnegie Mellon, and has sort of stayed in touch with a group at Carnegie Mellon throughout his career. Went to NCAR and worked with Phil Rush, actually, who was the last speaker, or the speaker before him in this geoengineering series. Let's see if I can get this right. Then you went and you were a research scientist at Harvard for 6 years, I believe. Went to Canada and was a faculty member at University of Calgary, and then returned to Harvard a couple of years ago and is now a professor there. He also runs a startup company in Canada, Carbon Engineering, which he says he's going to now transition to being completely full-time academic, and that's a very varied career so far. So with that, I think.
Thank you. Thanks very much.
You, David.
I think it's great to be here. So I'm really happy to have questions and interruptions. This is a topic that is. You can't avoid talking a little bit about the public policy and ethics of it, and I'm happy to do that even in this talk, which is more technical. And I think that the underlying reality is that the basic knowledge that these things could be done is very old, but was for a long time a kind of taboo in the scientific community that said that we shouldn't talk about them. And so just to give you some sense of that, the very first high-level report that went to a U.S. president that had the basic climate science right went to President Johnson when I was 2 years old, and it had all the kind of basic elements that we now know are correct that tell you there's a climate problem. And I think quite bizarrely, in hindsight, it tells you how the science has changed much more slowly than our sort of social science of how we think about things. The only thing that report actually suggested doing about the problem was geoengineering. But it's suggested in a completely nutty way. But there has been essentially no organized research on this topic, and that changed a little bit maybe almost 7 years ago or so when Paul Crutzen published an article. Didn't actually say anything new, but just the fact that he published it started to open up the space for people. It was more socially acceptable for people to do research. I've ended up doing quite a lot of research here, really just because nobody else was doing it. And now there is the beginning of serious research programs. In the end, as you all know, science kind of follows the money. And the Europeans now have like $20 million or so of real organized research programs, but there's not really any in North America yet. So I'll give you some overview of some of the really kind of basic science story and some of the basic questions that I think we don't know the answers to, but we have some preliminary answers. As I said, feel free to interrupt. So I think it's useful, so I'm only going to talk about solar radiative management or solar geoengineering. And I believe it's useful to think about these things as really two pretty different questions. And for now, I'm just going to plunge right into the science, not talking at all about why you do this or what the larger kind of governance questions. One question is how you would engineer a given radiative forcing. How well you could engineer it, what the risks and side effects of engineering that radiative forcing are. So that's essentially one part of the problem is making the radiative forcing in some way. And the other part of the problem is understanding how the climate responds. So in general, if we're making a shortwave radiative forcing, which was what most of us have been thinking about because it was the easiest thing, but Truda is thinking of something different, which is much cleverer. But in general, if you're thinking about a shortwave radiative forcing of reducing the insulation effectively, it's clear that cannot exactly compensate for the effects of CO2. Indeed, it obviously isn't going to in any way compensate for the geochemical effects of CO2, like, say, ocean acidification. But the question is how good a job you can do compensating the climate change that comes from CO2. And the answer, I think, is actually surprising to me anyway. It's been very surprising how good it is. So I divide things into thinking about the risks and the efficacy. And the risks I happen to have listed are for stratospheric sulfates, but there's lots of other technology. But the risks to me, in the way I'm thinking about it, are the things that are kind of the direct side effects of the way you do, the particular way you might do the radiative forcing. So if you put sulfate aerosols in the stratosphere, for example, some of them are going to rain down the troposphere, and they're going to add to air pollution and kill people. And in fact, myself and Steve Barrett at MIT are calculating how many people will be killed. So that's one chain of risk. And obviously, there are other ways you might engineer the radiative forcing, like solar mirrors, where the risks, direct risks, would be much, much smaller. And then there's this set of questions about what I would call efficacy, which are really questions about how well this does or doesn't compensate. And I've given a list of some of the major issues. So kind of just jumping into some science. A standard assumption for a very long time here was that we would do this by kind of copying what volcanoes do. Volcanoes put SO2 in the atmosphere, in the stratosphere. SO2 doesn't make particles. It has to oxidize to H2SO4 to do that. And that takes a good fraction of I just realized I need to have my watch. That takes a good fraction of a month, a couple weeks. And once you've made H2SO4, then that wants to condense onto particles. So the standard idea is that you're going to put SO2 in the atmosphere. And it turns out that it doesn't work very well. Even though that had been the standard idea, nobody had ever done any careful calculations about how well it worked. The problem is that if you continuously put SO2 in the stratosphere, almost all of the sulfuric acid, the H2SO4, ends up going to existing particles. And that makes it very, very inefficient, because there's two phenomena. Well, there's actually three phenomena. There's two important ones. One is that just simple Mie scattering. So if you have a physics background, you know that there's this, you can calculate the scattering of small particles. And if you calculate the scattering divided by the mass, so essentially the efficiency, mass efficiency of scattering, that has a strong peak around a tenth of a micron or so. And as you get much bigger than that for this index of refraction, you end up having really terrible scattering efficiencies. So big particles just don't scatter well. So that's one problem. The other problem, of course, and that's what's on the right here, is the gravitational settling velocity in kilometers a year, which is the right kind of units, because stratosphere is a couple kilometers. You think about the kind of depths you care about. If you get to settling velocities that are much over a few kilometers a year, then you're getting very quick removal. And so both those problems mean that as particles get bigger, they get much less efficient per unit sulfate at scattering sunlight. So there were a whole bunch of estimates for what the total radiative forcing would be, 0 to 4 watts per square meter here versus the sulfur injection rate. And there's some early papers that kind of had some estimate like this. But this work that was done by Deborah Weisenstein and the group at ETH found that if you made a more serious model, at least Deborah's high-quality 2D model, and actually modeled the aerosol microphysics, you get this really strong saturation effect, where you can put as much as some absurd 20 megatons sulfur a year in the stratosphere and have quite a low radiative forcing, because you're just putting more and more sulfur, making the particles bigger that are falling out quicker. So we came up with a potential solution to this. This is this Pierce et al. Paper. So some of the same overlapping group of people. I sort of put this group together. And the idea is simple. It's that if you directly put H2SO4 from an aircraft, let's say, you can easily control, just by controlling the addition rate effectively, you can control the size of the particles that you get. And so Jeff Pierce had a very nice particle nucleation scheme. He's an aerosol scientist who came out of the CMU group. And so we kind of coupled his aerosol scheme to the same Deborah's model, and essentially gave Deborah's model, instead of giving it SO2, we gave the 2D model the actual particle size distributions that we're getting out of the plume a couple days after emission. And it makes an enormous difference. That kind of gets you back to this theoretical line, and even better than the theoretical line that people had, because you can now have a decent job of controlling the size of the particles. Whether this really works in a more 3D world or in the real world, we don't know so well. But these are very early days. I think one of the issues, there's general true of this field, you have to worry about groupthink. So it's fun to publish an early paper, and this may actually have made, I think you would argue, a major advance in the sort of basic ability to do stratospheric sulfate geoengineering if you ever want to do it. But until many more people think about this and critique it, I wouldn't necessarily have that much confidence that it's correct. But I just want to give you some idea about some of the emerging stuff at the kind of atmospheric science physics interface that helps you think about this whole set of questions about how you would do the radiative forcing. Yep?
Quick question. Can you get the particles to the altitude that you want with an airplane? Is that practical? Or?
Yes, turns out to be easy. So separately, I don't know if I have it here. Jay Apt and I gave about $100,000 to Aurora Flight Sciences, which is a leading company that does altitude aircraft, and I've worked with Jim Anderson, helped to fund it to do science. And I can't find that paper right now, but it's on my website. And Aurora did a pretty complete study. So we told them, don't think about atmospheric science, just do a complete traits-based study of the cost to get either 2 or 5 million tons a year distributed to altitudes up to 100,000 feet. And they looked at a bunch of different things, different aircraft designs, balloons, and so on. Bottom line is it's absurdly cheap and easy to do this. If you wanted to get started, you would probably use Reagin Gulfstream G5s with F117 engines on them, and you can do that for a cost of about $1 a kilo. Which, when you do the math here, means that you do the whole thing for $1 billion a year, which is incredibly cheap. And it's easy for the science community to kind of assume that that's a good thing. But it's not necessarily a good thing. That means that unilateral action by small states is possible. These costs are absurdly small compared to the overall damages and costs of cutting emissions. And effectively, the costs are so small, it is a public policy problem. This is a risk-to-risk problem. There are risks of doing it. There are risks of not doing it. But the costs are so small, they're basically not going to enter for most of the schemes we've talked about, or that I'm talking about. I think the bigger issue is how you can improve on the effectiveness or decrease the risks. So we began to think about other particles other than sulfates. There are other, why do you have sulfates? Water vapor would work fine, but water droplets evaporate too fast in the stratosphere. The reason the sulfur is there is essentially to keep the water from evaporating. In principle, you could use other materials. We've done a little bit of simulation. Deborah and I are in the middle of simulating alumina right now. Alumina has a very high index to refraction. You can make smaller particles, and turns out that there's been a lot of work done back to the 70s on the environmental impacts of alumina in the stratosphere because it's a product of space shuttle exhaust. So it was sort of a good one to start on because there's a plausible reason that it actually might have lower risk. I'm not sure it does, but there was a plausible reason we thought it did. Right now the results seem to be the opposite. So there are plenty of other things you could look at. I'll show you one that really is science fiction in a sense, but it gives you a sense of what the limits are if humanity wanted to do this. So this is a paper I published in PNAS 3 years back or so, and I just want to give you a sense for a more physics science audience of what the limits might be, not that this is the outer limit. So it's possible to make engineered particles. And you could make engineered particles that actually levitate using something called a photophoretic effect. It has to do with the fact that different surfaces have different probability that an air molecule will thermally equilibrate with a surface. And so if you make a thing that has surfaces that are different, you can have quite strong levitating forces. This is not a new idea. It goes back to Ehrenschaft in 1910 or something. There are tons of papers on photophoretic levitation in interstellar disks. One of the new ideas that was in this PNAS paper of mine, I guess, are that you need some orienting torque to keep a little flying saucer thing like that in the orientation you want. And what occurred to me is that there are, of course, forces other than gravity in the atmosphere. So we have the atmosphere almost everywhere has an electric field of about 100 volts per meter. And of course, it also has a magnetic field. And so the trick here is that you could make a thing that was what a physicist would call an electret, has a permanent electric dipole moment, and that makes it want to orient. And so in this particular design that's in that paper, you'd have sort of a 50 nanometer thick thing with a thin aluminum layer that was thick enough to have good solar reflection but reasonable infrared properties. and it would self-orient with barium titanate, which is a very common, widely known electret. In principle, if you could build these things, and there's no question that theoretically you could do it, but if you could build them at interesting cost, the advantages might be, if that's an advantage, and it's not clear it is, longer atmospheric lifetimes. A big advantage might be these things float up to the top of the mesopause, so they would be out of the way of the stratosphere, so they would not directly affect ozone. But maybe they do something else that's terrible. I mean, you know, the advantage of thinking of something new is you solve one problem you know, but then maybe you create some other problem you don't know about. It's also theoretically possible to arrange for these particles to go to one part of the atmosphere, at least zonally. There's some clever tricks you can do that, but it allows you to begin to think that you could do some zonal tuning. So you could put more of the radiative forcing near the equator or more near the poles, depending on what you wanted to do. And finally, one of the problems with sulfate aerosols or any of these little droplets is a lot of the scattering of light is forward scattering. And so you change the ratio of diffuse to direct sunlight. And that affects the way plants grow and so on. In general, it makes plant growth more efficient to have the same amount of insolation but with more directed diffuse because you're not saturating some leaves and leaving other leaves unserved. But that would still have a big environmental impacts in changing the relative competitiveness of different plant species. You can see this. So during the Pinatubo eruption that put 8 roughly million tons of sulfur in the stratosphere, you actually see an increase in productivity globally, ecosystem productivity that has to do, we think, partly with this direct diffuse illumination problem. There are several papers that have looked at that. But this, in principle, allows you to solve that problem to the extent you think it's a problem, because a little flat thing like this just has backward scattering. To pick up on this idea from the Pierce et al. Paper, you know, smaller particles seem nice for the optical properties, but smaller particles are actually worse in terms of surface area per volume, and it's the surface area that matters most directly for stratospheric ozone impacts. So this just gives you a sense of what the ozone impacts are. Recently, Kate Rickey, a student I share with Dan Schrag, and I and Deborah Weisenstein have been starting to, and Jim Anderson at Harvard, think much more carefully about the ozone impacts. And mainly what we've done is convince ourselves the problem is much more complicated than we thought. And there are lots of ways the ozone impact could actually go in principle either direction. So it's not clear necessarily that adding particles to the stratosphere make less ozone. You can arrange to make more as well. There are some pretty complicated feedbacks here. So this is just a little hand drawing I had that we're in the middle of working on papers. But if you think about it, the local ozone loss depends on local water vapor, stratospheric H2O, local temperature in the stratosphere, and the surface aerosol, the sulfate aerosol density, the amount of surface area per unit volume of these aerosols. And actually, I'm not going to talk much about it. Jim Anderson and I are thinking about actual real in situ experiments in the stratosphere to measure the stratospheric chemistry and understand it better. But if you think about the different things that feed back on these, what you're directly doing if you add SO2 from SRM, what you're directly doing is adding aerosol. That's what you know you're doing. But there's all sorts of indirect effects. So you're changing the temperature through changing the radiative properties, but you're also, the whole point of this is to reduce the surface temperatures or reduce climate change. And that, by changing the surface temperature, will change the stratospheric temperatures a little bit indirectly, but also, in a very big deal, it'll change the tropical tropopause temperature, which changes the amount of water vapor that gets in the troposphere. And that feedback is hard to know because we actually don't understand as well as we would like to what controls stratospheric water vapor. So there's a lot of feedback loops. And I think, in general, all the papers that have looked at the ozone impacts of geoengineering have kind of assumed away most of these feedback loops. So they haven't looked at the water vapor change or some of the temperature changes. And we're not attempting to just run a GCM because we don't really believe them. We're just trying to really think through the physics of the different feedbacks and try and think systematically about which are the big and low feedbacks here and what knobs there might be to manage the impacts. I should say in context, there's some risk that Jim Anderson is worried about, that there's evidence, which is disputed, that as the world gets warmer, we're going to get more water vapor intrusions into the lower mid-latitude stratosphere, lower stratosphere. And if we do, and you did geoengineering, you could get pretty big ozone losses. Maybe. I mean, this is really kind of new and disputed science. Nobody knows the answer. So just to give you a very rough sense, these are some of the risks. In general, this field is new enough that I think we're quite a long way from anything that looks like systematic risk assessment. We have kind of individual papers looking at risks here and there, and that's about it. Let me talk a little bit about efficacy. So there's some sort of standard wisdom in this field which just turns out not to be true. And so one of it is that somehow this idea of adding, say, sulfides to the stratosphere only works to bring global temperatures back into, say, to pre-industrial or whatever you wanted, and won't help with precipitation. Or there's an idea that it really only works at a global level and doesn't work regionally. And it's really not so simple as that. So my student, Juan Moreno Cruz and Kate Rickey and I set out to really be quantitative about the extent to which some change in the solar forcing actually really compensates for climate change at a regional level. So what we did is there's a whole bunch of climate impact literature that uses these standard regions that have come to be called the Georgie regions. There's 23 of them or something, I don't remember. You can count the number on this list here. And so we ran, in this case, the climateprediction.net ensemble set of models under a CO2 ramp configuration. I can give you more details if you want. And then analyzed changes in temperature and precip on each of the regions. So if you're thinking about climate impacts, I mean, in the end, to do real climate impact analysis, you actually have to dig down and figure out what you care about. It's not a scientific question. It depends on the values of what you have to care about. But a not bad common approximation in lots of the climate impacts literature is to think about the fact that the impact is proportional to the amount that the climate's changed compared to the pre-existing variability, and then it might be that squared. There's a lot of evidence that impacts are quadratic. So that, you know, if you raise the temperature 4 degrees, it's, you know, more than twice as bad as raising it 2 degrees, or change precip similarly. But also that changing the temperature 4 degrees in a place where the interannual variability of temperature is 4 degrees is not such a big impact as it is in a place where the interannual variability is 1 degree. So the units here are the change in the quantity, temperature or precip, divided by the interannual standard deviation. So they're normalized to be dimensionless units. So this shows you for all these regions what happens to temperature in a world with roughly the point of CO2 doubling and with a certain amount of SRM. And the same for precip. And then you can see the standard deviations on the bottom. So first, one very important thing to say is a statement you often hear that this technology necessarily decreases precip. That's not quite true. What is true is that it definitely, precip in a sense responds faster than temperature. So if you decided that you wanted to bring, if you start with a climate, increase CO2, and then did SRM to bring the temperatures back to pre-industrial, which is what a lot of models simulate, if you did that, then you end up with precip globally lower than pre-industrial. But that's almost certainly a completely nutty thing to do. Nobody has really thought through public policy suggesting we do that. You could just as well say that you start with a climate, increase CO2, which increases precip, and then do enough SRM to bring precip back to pre-industrial, in which case you'd leave the temperature a little bit warmer. Scientifically, those are equivalent statements, and it's a public policy decision, which we do. As I'll argue later, you probably don't want to do either of them. You want to do something much more lenient and just do a little bit of SRM so you have a bigger chance that the benefits outweigh the costs. So you can think about this. The response of climate models turns out to be very linear. Whether the response of the world is so linear isn't clear, but climate models are amazingly linear. Climate modelers typically don't agree with this, and when you write papers saying it, they complain, and then you have to publish appendixes showing how they're linear. I've done this thrice in my career, but they're really linear. In the regions that we're using here. So just pretend I have two regions. This could be India, South India, and North India temperature, or it could be North American temperature and South Indian precip. It doesn't matter. Just two regions in my climate model. And so CO2-driven warming is a roughly linear response to CO2, let's say, or to radiative forcing, actually, will change those in some particular direction. And SRM will change it in some other direction. And if it was exactly the same direction, then it would be perfect compensation, but it isn't. So you can think about some residual climate change, and you can start to think about the public policy, the trade-off, that you could make everything just perfect for region B, but region A is too warm if that was warming, or you can do some supposed optimum. But the question here, these are just drawings. The question is, what's the actual angle? Fundamentally, the radiative forcing from CO2 is just not the same physics as the radiative forcing from putting solvates in the stratosphere. And the question is, to what extent is the response to those forcings similar? That's the objective question. And you can think about this, since it's roughly linear response, as in this, well, 22 times 2 if you like temperature and precip, so 44-dimensional vector space. How far apart are the two vectors? Because in the end, right, I've got all those different places. They're all responding with different coefficients, but linearly. So I can make a big vector space of all these things. And I could ask myself, what's the angle between the CO2 vector and the SRM vector? That's a kind of basic measure of how good the compensation is. And if you'd asked me to guess, I would have guessed the angle was like kind of 30 degrees, that SRM was useful in reducing climate change, but really didn't do a very good job. The actual answer we got was, I think, kind of stunningly good. I still find this very surprising. You got all these regions, you got to figure out how to weight the regions. So you could, you got to decide if you're weighting them by money, if you're an economist, or by area, if you just maybe care about the natural world, or by population, if you just care about people, we call it. And so we don't have any opinion about what's the right answer, but objectively, you've got to think about the different answers, because there's no magic way to weight them. So what this is telling you is, if you're looking just at temperature and you choose the amount of geoengineering that does the best job of compensating temperatures everywhere in a kind of least squares sense, and you were weighting things by population, the angle is 3 degrees, which is basically perfect, which I still find very, very stunning. So the other way to say it is, I've written up there, for example, if you choose geoengineering to minimize changes in precip, you can cut the precip by 87%, like this 13% residual on a region-by-region basis. So I find that very surprising, because the radiative forcings really seem quite different. And I think it's interesting to think about why this is true and why it might not be true. I don't think this is just an artifact of this model. To be clear, I don't believe these exact numbers. If you used a different model, you'd get slightly different numbers. But broadly, my sense is that most models have responses that are somewhat like this. And it's not exactly clear why. I should say that in the end, it's not precip that matters so much to most impacts. It's really E minus P, evaporation minus precipitation, the kind of net hydrological forcing. So I'm going to just go through a couple other recent science papers and then kind of step back a little bit and talk about where this is going. But I just want to give you some sort of, since this is a geoscience audience, some sense of where people are going. These are papers that I think are kind of easy to write because they're just playing with models. The hard part is figuring out what are the actual trade-offs and how we would know something more than what's in a model. But it can be fun to play with models. So one of the questions is, how well would non-radiative forcing help? So could you optimize a little bit by choosing how to distribute the top of the atmosphere radiative forcing in order to achieve some objective? And obviously, the climate is all coupled. So it's not as if you can treat each region separately and just adjust its climate independently, because winds advect moisture and temperature across the world. But it's still interesting to ask how much you could optimize. So I've been working on this with Doug McMartin, who's a control and dynamical systems guy from Caltech, and then a bunch of us who've done some climate modeling. And so in this particular paper, we had we ran climate models with three different top of the atmosphere radiative forcing. So like one that was uniform and one that was peaked in the north or peaked in the south or peaked in the equator. So three different choices for how we do top of the atmosphere radiative forcing in a north to south sense. And then also we gave ourselves 4 seasons we could work with. So we could peak it in any one of the 4 seasons. And so this just shows you, for example, there's a lot of worry that we're losing sea ice. So the question is, how well could you restore sea ice while doing maybe the minimum amount of overall SRM? That would be a potentially interesting policy question. So this is, for example, is in this climate model run, the minimum amount of northern hemisphere sea ice versus tropical precip, just to happen to plot things. And these dots are all the different model runs. You can get a look at the result. So the bottom line is that doing this sort of optimum system is significantly better than, on many metrics you'd care about, than doing just a uniform, dumb 1%. It turns out it's especially good at minimizing who's worst off. So if you just look at grid point by grid point at which grid point is worst off, we actually make the worst off less worse off by quite a lot. How realistic this is, we can debate. But I think the central point is that if people actually got going doing this, you wouldn't just do some kind of dumb one-time radiative forcing. You would do some tuning, both in response to what you actually observed, for sure. And a separate set of papers not yet published, we've been dealing with the sort of feedback question. So, you might argue we don't know the climate sensitivity models or the world, which is true, but we're not making a one-time decision about whether or not to geoengineer. Let me say that. Yep.
Just for clarity, can you reassure me that you're talking about changing the distribution, for example, of the sulfate with latitude?
Yep.
And trying to maintain that?
Yep.
By, letting it evolve, but then putting it up where you...
Yeah, whether you could do that with sulfate or not, we don't know. So you could clearly do it with some kind of magic orbiting solar system. With sulfate, we're building we're building additions to Geo's chem model that having a better sulfate aerosol model for the stratosphere to attempt to begin to do at least one step more realistic simulations of how you could manipulate the sulfate in 3 dimensions. So nobody's even done that once yet. And so I wouldn't claim that you could necessarily do this with sulfate. I mean, you could, remember though, it's a linear thing. So can you make an exact distribution like this? No, but you could probably make one that was a little more in the equator than the poles, for example. And the final thing that we find out here is no surprise. You find that if you really want to make more sea ice, you want to peak it in the northern hemisphere over the summer, which you could kind of... Absolutely, absolutely. So most of the models that we've run, we assume that you're injecting in kind of plus to minus 20 or 30 degrees at about 20 or 25 kilometers altitude, basically in the tropics, counting on Brewer-Dobson to do the rest. That's the sort of base case model that's in Pierce et al. But you could imagine, yes is the answer. Another interesting question, I'll just show one slide from this paper. So in policy terms, people often assume, I'm not sure I buy it, but it's a common assumption, that you would do this stuff only if you found out the climate sensitivity was very high. So we don't know the climate sensitivity, we're gradually adding CO2, we can't just back up, CO2 accumulates in the atmosphere. We'll gradually find out how sensitive the climate is. And one way to think about this is you do it in an emergency situation, which I actually don't like that phrasing. I'm using phrasing other people use. I think it's a bit of a rhetorical trick. But the idea would be that you do this in a situation where you found out the climate was extremely sensitive to CO2. And so Kate Rickey and I forget who else on the paper, Granger Morgan and Ingram, wanted to look at the question of whether or not worlds that had higher sensitivity have different responses to SRM. Because one possibility is that it turns out that the worlds that have high sensitivity don't work for SRM for some reason or work less well. And so you're being over-optimistic if you think that you can just use it in a high-sensitivity world. So the climateprediction.net system that presumably many of you know about, they've built ensembles of climate models where they have hundreds of models with different physics. They've systematically perturbed the physics of climate models and they run these monster multi-model ensembles. So we used those and used those with a geoengineering and a base case simulation, and then selected the models that were very high climate sensitivity in the climate sensitivity distributions you see from that group, and asked basically, is the response to SRM different? And the answer is not much. But there's a Nature climate change paper about it. Just to say that people are just beginning, I haven't done any of this work myself yet, to go a step beyond looking just crudely at temperature and precip and actually start to ask about climate impacts. So if you think about climate science and policy overall, there's a huge amount of physical science work understanding the climate system, its response to CO2, and so on. There's a huge amount of work that appears in IPCC Working Group 2 on what are the climate impacts. And there's basically been close to no effort, 3 papers maybe, that have attempted to, for some impact we might actually directly care about for humans, think about how well SRM might work or not work to reduce that impact. So this is one example from a paper that Julia Podgratz and Ken Caldera, and it's really relying on the crop temperature models of David Lobel. And And those models are in turn really tied to observations in a way that I think is very, very strong, although there are people who argue about them. And those models fundamentally say that one of the big impacts of climate change will be peak temperatures during the germination season. And indeed, Lobel's models, this has nothing to do with geoengineering, suggest that we're already losing several percent of global productivity because of that. So these are some simulations which do show that when you do SRM, you can get a significant amount of productivity back. That is, that the world that you have, a world that is a high CO2 world with SRM has significantly higher crop productivity for most important crops in most places, not everywhere, than a world with high CO2 and no SRM. So I've talked a little bit about some measures of efficacy. Serious work to look at efficacy is really just beginning, I would say. There's all sorts of stuff that hasn't been done. There's easy papers just lying out there to be written looking at variability, for example. You might expect, so one of the things we all know that's a risk of climate change is that the hydrological cycle gets more variable as it gets more intense when you add more CO2. Although there's a slight counter effect that you're decreasing the pole to equator gradient. But if you do CO2 at SRM, you don't increase the hydrological cycle so much, so you're going to tend to dampen the variability, I think. Nobody's published a paper saying that yet. I did get Kate to look at that, and it did turn out to be true, and it's like a tiny footnote in one of Kate Rickey's papers, but we need to actually look at it carefully. And I've heard other people who I respect argue that it won't be true, so I don't know. This is pretty much all about models so far, and models are not the same as reality. Of course, these are the same models mostly as we use to understand the risks of increasing CO2, but you really do have to think about how you manage this problem when you only have one planet and you don't know exactly how the system will respond. I think a fundamental, so a couple things to say. If you asked me personally to make a choice between implementing geoengineering now with, say, sulfates to compensate for the entire effect of all anthropogenic greenhouse gases, and I made a one-time decision for like 100 years, or to abandon the geoengineering forever, I would choose abandonment. So I think, if you think about this as a one-time decision like that, it's almost certainly nutty to do it. The uncertainties are just very, very large. And it's also true that compensating away all of 2 times CO2 is almost certainly a bad idea. But that is not the choice we face, not even remotely. First of all, the main choice we do face now is should we actually have a serious research program. But beyond that, there's by no means right that you should compensate all of 2 times CO2. I'll show you some figures to show you why I think that's foolish. And if you did it at all, you would presumably do it in a gradual way. And I'll show you a specific kind of example for what I mean by doing it in a gradual way. And you would monitor looking for side effects as you went. There's another one of the papers with Doug McNamowski, me, Ken Caldera, that was published in Earth, the Royal Society Journal, EES, Energy Environmental Science, that looks at some of the signal-to-noise questions of when you could start to detect a signal and how you might modulate your way up to give yourself the best chance to detect bad side effects before you saw anything. So I think in reality, you do something like that. You wouldn't just flick a switch and turn it on. So first of all, let me deal with this question of I already gave you this idea about impacts. But let me just give you this sort of basic argument that it makes no sense to do 2 times CO2. For some of you who aren't reading the literature on this, this might be so obvious it's snoozy. But what's amazing is most of the climate model simulations that have been done have assumed effectively that SRM deals with the full 2 times CO2. And then they've talked about the risks of SRM as being what's left over after you deal with 2 times CO2. And that was a convenient climate modeling thing to do because it gives you good signal to noise. And as a piece of science, there's nothing wrong with it. But if people translate that in their heads to something that relates to public policy, it's dumb. And that's the key point I'm trying to make here. So benefit saturate. This is actual real data. The next plot I'm going to show you is imagined data. But this is real data. It's that actual variance number on a grid point or a grid point model. And so the point is, this is some reduction in this mean square temperature and precip deviation. And this is versus the reduction in solar constant. So I'm getting benefits because I'm reducing harms. And so as I start here, reducing the solar constant, I get this pretty steep reduction in the overall change. But at some point, it peaks, and then it gets worse and worse. if I reduce the solar constant by 8 or 10% for 100 years, according to 2 papers, I get yourselves back to the neo-proterozoic snowball Earth and kill everything on the surface. I'm not suggesting we do that, but it's clearly not true that if some geoengineering is good, lots of geoengineering is good. This is not the optimal amount of geoengineering. This is the point where you get the absolute minimization of change, but there's also going to be bad side effects of geoengineering. This is a made-up figure. But presumably, ozone loss or various other bad side effects are probably going to grow faster than linearly. So if I add up, this is just sort of like Econ 101, if I add up something that kind of has a peak like that with something else that's growing faster than linearly, this number was invented. This is just my mathematics. I just wanted a curve here. I'm going to have, and I add the two together, and then I'm looking at something more like the optimization between costs and benefits. The peak is for sure going to be quite a bit to this side. So that's the basic argument that says you might not want to do 2 times CO2. There's also a kind of policy component, which is I think we still want to cut emissions quickly. At least that's what I think we should do. And so I think leaving some of the effect uncorrected so there's more of an incentive to cut emissions might be good policy. So overall, my sense is that if you actually want to do this, you want to do a relatively small amount of it. So let's make a specific proposal. Let's say you wanted to partially counteract CO2-driven climate change, and specifically, you might decide to reduce the rate of warming by 50% starting in 2020. Let's just put the numbers in for what that means. So that means in 2020, you do nothing, but at the end of the year, you've got to put in enough sulfate aerosol to correct for half of the radiative forcing increase. That turns out to be 25,000 tons of sulfur by the end of that first year. And that takes 2 of these Gulfstream aircraft, just to give you a sense of how easy this would be to do. Single base. Each additional year, you've got to keep adding on. So after 10 years, in 2030, you're putting in roughly a quarter million tons of sulfate. At that point, the sulfate is barely up to the natural background, but not quite. So it's important to say you're starting slowly. You're starting well below the natural background here. There's a natural background of sulfur getting in the stratosphere anyway. And if you do that for 50 years, you're up to still just under 1 million tons a year in 2070, which I don't want to claim that this is no risk, but the point is we know some things that are empirical, not models, that tell us with some confidence what the risk might be. Because remember, Pinatubo is 8 million tons in 1 year. So that gives you some sense. Pinatubo had lots of impacts, but it gives you some sense that we can say something quantitative that is tied to real observations and not just models, not that I don't trust models necessarily, about what the impacts might be when we got up to, say, 2070. And that's a long time. I mean, that cuts the rate of warming in half for half a century, which has real benefits to humans who are alive now. And I think that's the sort of important case for how to think about this. Here's a little fun.
Sorry, are those costs
Yep.
per year? 700 million?
The cost per year of doing that, if you did sulfur all the way out, you can look up the ERL paper, but think of it as being $1 billion a year by 2070, round numbers. But you probably switch to some other kind of aerosol. This is just, I actually want to be a little bit numerical about it. There's a common statement that, for instance, Ray Pierre Humbert, who's a very, very smart and thoughtful guy, makes, which is that once you start geoengineering, you have to do it forever. So this is just not true. It just isn't true. I mean, Ray knows it's not true. There are big benefits if you do it only temporarily. That's not to say that you should do it. There are very good arguments not to do it. But the argument that if you do it, you have to do it forever is not one of them. So many climate impacts depend on the rate of change. And so if you did SRM, this is millions of tons a year sulfate. So this is the same ramp I showed you up to 1 million tons a year and then ramping back down towards 0. So the point is, by the time you get back down to 0 here, in a simple climate model, here I've got radiative forcing. I just use a simple impulse response function model. I actually did this on the train this morning. By the time you get out to here, there's absolutely no benefit from SRM. Basically, you stopped SRMs. There's no benefit. The point is, long-term climate change depends on how much CO2 we put in the air, and if we want to reduce the long-term climate risk, we have to stop putting CO2 in the air, period. Nothing about SRM changes that. But it's also true that if you do SRM temporarily, you can flatten out the peak and reduce the overall rate of change of temperature. And there's very strong evidence from the climate impacts community that the rate of change of temperature has a big role in setting impacts. So you can meaningfully reduce impacts if all you do is do some, what we might think was peak shaving. You do geoengineering for a while, up to the point where you brought emissions down to about 0, and then you taper geoengineering back down to 0. And that may or may not be a good idea, but it definitely reduces the standard measures of risk, and it definitely doesn't commit you to do geoengineering forever. This should be a progressive thing. You would never just start doing it. As I said, you'd start with lab modeling, with impacts. You're going to find problems. Then I believe that you should start thinking about specific, very small experiments that get at specific atmospheric processes. These are not experiments where you're trying to actually perturb the climate. They're experiments in which you're trying to find out whether a specific process works the way you think. So Trude has been looking at this question of whether some particular nuclei would reduce cirrus in some place. You could go out and do an experiment on a scale of 100 square kilometers, in principle. And that experiment, the goal of that would not be to manipulate the Earth's climate. The goal would be to understand whether a specific piece of Trude's model was correct. And similarly, Jim Anderson and I are beginning to do engineering and science work, developing an experiment that would put water vapor and or sulfate in a small volume. Think of it as being few cubic kilometers. So this is we're talking about 1,000 kilos of water, so less than one transatlantic aircraft flight. And we would measure some of the specific risks that we don't know well enough about the ozone chemistry interactions. That would be a manipulative experiment in the atmosphere, which is an unusual thing. And there are real issues about how we regulate and govern those. But it's pretty clear that they don't alter the climate. Their goal isn't to alter the climate, it's to do processing studies. Quite separately from that, you could do minimal scale deployment. At that point, it's not an experiment. At that point, you are manipulating the planet, and we need some governance system that manages that, and I don't know what it is. I've got suggestions. And that's where these paper, for example, the Baknamowski paper in EES deals with the signal-to-noise question of when you could first detect a very minimal deployment like this. And then only if you did that, you'd begin gradual deployment. So the idea, the point here is to say that hold on, the point is to say that to try and shake you from the notion that our choice is whether or not we should do this altogether. And I think the choice is really whether or not we do research and whether we begin, if the research pans out, which it may not. So one thing research may do is show that this idea is much worse than some of us think. And that's a healthy thing. It's good if we know that. So let me say a little bit, just on the closing three slides, about what my fears are. My fears are actually mostly not about the sort of narrowly conceived technical risks. I think those risks are real, but I don't think they're the big risks. And this is getting into a little bit of the policy talk I'll talk about in the afternoon. There is real potential for conflict here. The fact that it is so easy and cheap to manipulate the Earth's climate this way, if you gave that power to a completely unbiased, apolitical panel of people who had in some global Rawlsian democratic view of the humanity's best interests, and they had time on their hands to think it through carefully, then it's, I think, pretty likely that having this extra ability would actually be useful in reducing climate risk. But that's not the world we live in. And in the world we live in, you could imagine outcomes that are really horrific if different countries have different views about how much to do, and then as well as that, they have different, they have the slow and stochastic nature of political decision making. Just for fun, we've been doing these models where we do feedback control of the climate for fun, and we put delays in to show kind of that if politicians are slow making decisions, you can get oscillations, and you can, of course. So I think that you could have really horrific outcomes. There's also this question that is a little more fuzzy, that in some way this represents humans really officially making the planet an artifact in a way that's different from just making a mess, I believe. And there's actually was a series of articles between me and Brad Allenby where he argued they were the same, and I argued that there's a difference between making a mess and deliberately engineering. So a key thing is, what's the goal here? Everything I've been saying so far is to assume that the goal is somehow to minimize the risk of CO2-induced climate change. Scientifically, there's no goal. You just learn stuff. For policy terms, that's only one of many goals. Another goal might be to, say, maximize crop productivity. And if that was the goal, you might actually want more CO2 in the air and then do some geoengineering as well, permanently. I'm not saying that is the goal, but I'm saying we're going to have to deal with this question of what the goal is. Tom Schelling, I've been privileged to serve on a panel with him on this recently. He's thought about this for a long time. These are words he wrote in the 1982 National Academy Report on Geoengineering. And I mean, the whole report wasn't geoengineering, but there was a section of it on geoengineering. And I think Tom, and I checked that those were Tom's words. I asked him. I think he nailed it. Interest in CO2 may generate or reinforce a lasting interest in national or international means of climate and weather modification, and what's generated, they may flourish independent of what's done about CO2. Once we get into the business of manipulating the planet to get some outcome, then people are going to start to ask for different outcomes. That's what happens when you invent new technologies like this. And the people who invent the technologies don't get to decide how they're used. There's this whole easy out moral hazard problem that I think is often misconceived. I'm going to deal with that a lot in my talk this afternoon. I won't say much here except sort of the basics. That's the fundamental worry that everybody has. It's important to say that this is, to some extent, we're making an empirical claim here. So the opposite is possible. It's possible that pointy-headed scientists saying that we need to contemplate something this scary will actually encourage action. There are lots of ways in which you can argue that geoengineering might make the politics easier. Marky Weitzman has made these arguments. So I don't think it's simple to say that it necessarily makes it harder. You can make arguments on both sides. This does a better job, I think, than any papers capturing this idea. These Tom Tolles cartoons, the punchline is always at the bottom. So the search for breakthrough technology to solve climate change continues. This guy says it's a time machine that will take us back 50 years to when we should have put a price on carbon. Then this guy says, we better hurry up. And this guy says, no, it's the great idea about a time machine. It doesn't matter when you do it. And that captures some of the moral sort of hazard idea here, that geoengineering has some aspects of a time machine in the sense that putting carbon in the atmosphere, without one of the two kinds of geoengineering, carbon removal or SRM, putting carbon in the atmosphere is pretty much a one-way valve. On reasonable timescales, the climate change is just the integral of the total carbon we put in, period. And so in a sense, it's sort of marching forward in time, you always get worse if you're putting any carbon in. These things allow you some measure of time machine, some measure of ability to go backwards. Then, of course, there are all the actual side effects and risks, which I don't mean to minimize, but I think that the big issues are more how we manage those risks than the objective risks themselves, from what I've seen so far. Thank you very much.
One of the things that shut down weather modification in the 70s and 80s, that is weather modification for precipitation enhancement, is that you started to see some lawsuits. In other words, they might see the cloud and you'd get a tornado nearby.
Yep.
And that gets thrown into the court of law, and suddenly somebody is responsible for what used to be thought of as a natural event. So I can just imagine even the most innocuous kind of seeding of the stratosphere with sulfates that could maybe have nothing to do with thunderstorms and tornadoes. What jury is going to know that for sure? And what judge is going to be able to? Suddenly you're responsible for everything that happens. Me,
personally, yeah. That's why I get the death threats. Seriously, actually. But yes, that's exactly right. And so in the, for those of you interested, there was an article I wrote now 15 years ago in Annual Review of Energy and Environment, where I went back and read a bunch of these early reports. And I found some very interesting things. So there was this huge boom in cloud seeding in the late 40s in the US. I think it's pretty likely that essentially none of it did almost anything, but there was an enormous commercial boom of cloud seeding. And as a result, there was a huge number of lawsuits with farmers suing other farmers for loss of rain. And that was brought to Congress, and they formed the Advisory Committee on Climate and Weather Control, which, if you look at committee membership, is essentially leads all the way to the IPCC. That's the beginning of having a formal US government committee that deals with these topics. Because that committee that started in 53, if I remember my date right, that committee just kind of blends in to the committees that then had Revell on them and people in the mid-60s, the beginning to think about the modern version of what we call the climate problem, and on and on. So that's exactly where some of this started. I completely agree. And the liability concerns here have always been central. People have talked about the problems of managing liability from geoengineering back, in fact, to papers in the 60s, because there are papers in the 60s. So the idea is absolutely real and important. It's not clear. So recently, now this topic's got to be hot, and we have lots of people working on it. We're thinking about it. We've got some legal scholars at Harvard starting to think about this, and several other groups have started to think more hard about it. It is a head scratcher. It's certainly a real issue, but there is a lot of international. I mean, what we've been doing is probably just looking at other international liability regimes, from oil spills onward. There are lots of them. There's the Outer Space Treaty. Some of them sort of work. There are lots of ways you could go either inside current international, sort of what's called effectively the equivalent of common law, or by adding new laws like some existing ones that I think give you some potential to do it. There's also, this ties to the question of liability for CO2 change itself. So there have been attempts, including a very important attempt by a bunch of attorneys generals of US states to sue coal-fired power plants as a public nuisance. And there have been other attempts around the world that have some legal traction, none of them have succeeded, to sue some of the companies that have the longest corporate history of CO2 emissions for contribution to climate change. And you can learn a lot from those lawsuits. I would say this problem is not unique to SRM, but it's definitely a problem. But it's intimately coupled with the question of whether you can claim damages for the CO2 emissions. And there's also some possibility that we've been investigating whether you could sue because SRM wasn't done. So if you're an Indian farmer and you have good science to suggest that doing some SRM would have saved your crops and the Indian government knew it, can you sue them to argue you should have done it? It's a lot of room for lawyers.
There's another question in the back here, I believe, and then oh yes, yeah.
So I was just wondering, is there any concern about terrorism arising from the ability to do this relatively cheaply, either state actors or non-state actors?
Yeah, so there's conflict that could arise because different states have different interests and do different things. But you're talking about like a terrorist action to do it. Is that what you mean? Yeah.
Well, holding hostage.
No, or not much. I've had some dinner conversations with Oliver Morton, who's a very thoughtful writer on these topics. He was a lead nature writer in Nature, and now is writing a book on this. I believe that it is theoretically possible to do this surreptitiously. I don't think it works in a meaningful way as a terrorist tool. There is a paper I've never actually read that Mike McElroy wrote a few decades ago about adding bromine to the stratosphere as a terrorist tool. So there's certainly ideas out there, but I just don't see them as being credible compared to other things that terrorists could do. Or, I don't even want to get to use the word terrorist. The people who want to threaten other people in that way could do.
Could you had, towards the end, you described basically what I could call an experiment. So, aside from the liability and legal issues, what's the scale of an experiment that would give you enough information, to help you improve your models going forward? And where would you do it on the planet?
So the point is there's these two very different things. There's experiments on processes, where what you're fundamentally trying to do is understand something that a climate modeler calls it part of their process model, that really is understanding how some microphysics interacts. And those experiments, some of them you can do in the lab, and some experiments you might want to do outside, but in general you do them at the smallest scale where you can get good signal to noise, because the objective isn't to change the climate, it's to understand the process. So the one that Jim Anderson and I are designing, we would distribute about 1,000 kilos of water from a balloon at about 25 kilometers in a kind of long plume that would be about 10 kilometers long and a kilometer or so wide. And we would be looking for the way that water perturbed the NOx chemistry to check our understanding of that NOx chemistry. And we would do it also with sulfates. And we basically, you might say, why not do it in the lab? The answer is, as you know if you know atmospheric chemistry, it's extraordinarily hard to simulate in that lab, because you've got the diurnal cycle, you've got strong UV, you've got, these are radicals, so if they touch walls, they're gone, and there are real limits to what we can do in the lab. So that would be a process study, and you can imagine process studies going after the kind of stuff that Trude has talked about as well. And those studies are not that different from current atmospheric observational campaigns. Their actual environmental impacts would be very small.
You would do them over populated areas?
We would do whatever was convenient because there's no, I mean, to be clear, this is less water vapor than one transatlantic aircraft flight. So just there's no, I mean, there are risks. Yeah, well, there are, I mean, I'm actually have some experience, and so does Jim, running real experiments like this. There are dangers, but the dangers are really not from the emissions, they're to the pilots. I mean, if you fly a balloon in the stratosphere, there's dangers.
Yeah.
The balloon payloads can fall down and kill people. And that's true whether it doesn't make any difference that it's a geoengineering balloon. It's the same if it's a telescope. So there are real risks that you have to deal with, but that's kind of normal risk management. And then, and this is really, I'll talk about this afternoon, this is really the point of the paper that Ted Parson and I published in Science a few weeks ago about how to do the governance. There's a very big difference in scale between those experiments which are inherently kind of want to be small, which are process experiments, and experiments that are a big enough scale to test large-scale atmospheric response. To do that, you've got to make the response big enough to see above the signal above the noise. And that turns out to be really big. So like 1/10 of a watt per square meter modulated over 10 years to see it. And at that point, that's not an experiment. I mean, yeah, I mean, you're basically you're doing it in a closed loop way. And I think at that point, you don't pretend this is a science experiment. It's kind of actively doing it and looking for problems. And I don't think there's much in between, because there's not a lot of reason to do things at the middle scale right now. So we propose that those get treated very differently, that right now you have a moratorium on doing the big stuff, and that you allow the small stuff under some scale.